In the last video, we started talking about collision theory, and we said collision theory talked about reactants forming products, and we had said that the two reactant molecules need to collide, and they need to collide with enough energy and the correct orientation, right? We needed effective collisions to lead to products. We also looked at an energy diagram or energy profile, which is where we graphed energy versus our reaction progress. So as we went from the left to the right along the x-axis, our reaction was proceeding. We start out with some amount of energy, we increase in energy to our transition state, and then come back down to our products. So our reactant energy, our product energy, this would be an exothermic reaction, right? Because my products have less energy than my reactants did. And we had said that the energy difference between the reactants and that transition state is my activation energy, right? That's the amount of energy that we have to put into the reaction for it to get to products. So when we say with sufficient energy, we mean energy that's equal to or greater than that activation energy. If we were going in the reverse direction, right? Some reactions do go in both directions, right? My reactants can form products, but then often products can go back to form reactants. And that's the case. Our activation energy is actually the energy difference then between the products on my graph and the transition state, right? If I was going in reverse, this is where I start out, this is where I end, and then my activation energy, this is going to disappear here, is going to be this energy difference, right, between reactants and products. So in the reverse direction, our activation energy is equal to my energy difference between the transition state, so TS, and the products, right? My products being my reactants in the reverse direction. Again, please note this is only for reverse. And not all reactions go in both directions, but a lot of them do. And we will talk quite a bit about reactions that go in the forward and the reverse direction this semester. So do note, for going the opposite direction, right, my activation energy, maybe we'll put it on here in purple. I just don't want you to think that I have two of them. It's one or the other. So this is EA in the reverse direction. We have talked a couple of times about temperature, right? If molecules are reacting at a higher temperature, then they have more energy to begin with. So at higher temperatures, a larger fraction of molecules have enough kinetic energy to overcome that activation energy. So at higher temperatures, remember, temperature was a measure of a substance's average kinetic energy. So when I say higher temperature, I'm saying they have a higher average kinetic energy. So at higher temperatures, a larger fraction of molecules have enough energy to overcome the activation energy, right? That's the energy hill, right? It's my barrier to reaction. In order to get to products, we have to supply energy that's greater than or equal to that activation energy. If we look at my graph, right, for my exothermic reaction, which is what this one is, in the reverse direction, it's actually less energetically favorable, right? My purple activation energy on there is bigger than my green one. So it does favor the forward direction the way that I drew it. If we increase the temperature though, we can increase the odds of it getting over that energy hill. We do have an equation that relates temperature to our reaction rates. Rather, the rate constants, but the rate constants are directly related to our reaction rate. So our equation is our Arrhenius equation. So this is used to relate temperature to reaction rates. More specifically, the reaction constant. Remember, our reaction constant is a lowercase k. We can also use it to solve activation energy. That's going to be part of our equation also. So it looks kind of weird at first. I am going to rewrite it a few times. So K, right, that's my rate constant, is going to be equal to a capital A, which I'll talk more about here in a second, an E, so the inverse natural log, raised to the negative EA, my activation energy, divided by R, which is our gas constant, and then T for my temperature. So that's the exponent. I'm going to move it up a little bit because it doesn't really look like it. That's my exponent on E. So taking A, multiplying it by E raised to those things I have in parentheses. So let's define a couple of those terms. K we know is my rate constant. A is called my frequency factor. And what it is, it's a constant related to effective collisions. Remember, not all collisions are effective, right? They have to have enough energy. They also have to have, which is going to be the activation energy here, but they also have to have the correct orientation. And then the actually sheer number of collisions matters, right? If I have lots of collisions, the odds of some of them being effective, right? There's more effective collisions than if I have fewer collisions to begin with. So this is a constant related to both the orientation and the collision frequency. So it's a constant related to collision, let's say effective collisions, it includes both orientation and the frequency of collisions. Right? They have to collide, they have to have the right orientation, and they have to have enough energy. So A takes care of those first two. EA is my activation energy, right? That's the amount of energy we have to put into it, so the sufficient energy portion. And then R is a gas constant. You have used the gas constant in 151 in your gas chapter, chapter 8. There, though, I warned folks that had me for that class that there was two different versions, so to make sure you use the correct version. Here we're using a different version than you used before. So in that chapter, you would have used 0.08216 liters atmospheres per mole Kelvin. In this one, we're going to use 8.314 joules per mole Kelvin. And be really careful to use the correct one. This constant is on the back of your periodic table, as is the other one. So please just be really careful to make sure you use the right gas constant. I always use the units on the constant to remember what the correct one is, right? So we're using this one. It has units of joules as part of it, right? There's a J there. And then energy, my SI unit is a joule. So when you're using the gas constant in an equation that involves energy, you want the gas constant that has units for energy in it. So please be careful to make sure you use the correct constant. And then T, capital T is my temperature. I warned you a bit back that remember a lowercase t is time, a capital T is temperature. So please make sure it's capital so we're not using the wrong variable. So temperature. And then my units do need to be in Kelvin. If we go back and look at my gas constant, my units are in terms of Kelvin. So I do need Kelvin. Oops, I didn't want a highlighter there. Temperature in Kelvin. We are going to rewrite this. It's not unheard of to use this form, but generally we're going to put it into a slope-intercept form. We're going to put it into the equation of a line. And don't worry about the derivation. I'm just going to give it to you. So rewritten. Let's do have this highlighted here. I don't think I need a hyphen there, do I? Rewritten. I'm going to have the natural log of k, right? Remember that E here is the anti-natural log, so we're taking the natural log of both sides. And then that's going to be equal to negative of my activation energy over R, still my gas constant. That's multiplied by 1 over temperature plus the natural log of A, that frequency factor. So if I was to graph, right, my natural log of my rate constant versus 1 over temperature, my slope is the negative activation energy divided by a constant. So we can actually figure out our activation energy by measuring my rates at different temperatures and graphing it. My y-intercept then is the natural log of that frequency factor. Sketching a graph for us. I'm going to have the natural log of my rate constant on my y-axis, and we're going to have 1 over temperature on my x. My temperature is in Kelvin, so units here would be Kelvin to the -1 or 1 over Kelvin, right? Log values don't have units, so I'm not going to show units on my y-axis. And then I have a negative slope, right? It's negative EA over R. So I'm going to draw my y-intercept here. And we're going to have a straight line with a negative slope over R. And then again, my y-intercept is the natural log of A. This equation works well if we have several data points, right? We do need to make a graph to be able to determine our activation energy. An accurate graph is probably going to need at least 4 data points, so this equation would work best for that sort of example. And I do have one for us. So let me make this a little bit bigger. So the first 2 columns are what you would be given. First 2 columns. So our temperature, keep in mind it is converted to Kelvin here. And then the rate constant was measured at those different temperatures. So if you were in a lab, you could actually get that data. The next column, what we're doing is we're taking our temperature in Kelvin and we're taking the reciprocal of it. So this number here is 1 divided by 555, right? If I was to take 1 divided by 555 Kelvin, that's going to give me that number. 1 divided by 575 Kelvin, that's giving me this number. So that column is just coming from taking the reciprocal of my temperature in Kelvin. My last column, I'm taking the natural log of my rate constant. So natural log of K. So if I was to take the natural log of this number, this is what we get. The natural log of this number, this is what we get. Once those have been calculated, we're going to graph 1 over my temperature on my x-axis, the natural log of K on my y-axis, and then we're going to get the equation for our line. We want our best fit line for that. So this is what the graph looks like. If you have a problem similar to this in the homework, you're likely going to be given just those 2. Again, you're going to calculate these values, you're going to calculate these values, and then you're going to graph them, get the equation of your line. Our equation of our line is right here for us. We know that our slope, right, is equal to the negative activation energy divided by my gas constant. If we scroll back up here, right, this is what our slope is equal to, negative EA over R. So what we're going to do is we're going to determine our activation energy. So determine the activation energy for a reaction using the data and graph above. So we're essentially just going to take our slope, we're going to set it equal to the negative of my activation energy divided by my gas constant, again making sure that we use the correct value for the gas constant, and then we're going to solve for activation energy. So my slope is this number right here, right? Negative 22287. It does have units, which we'll write down here in a second. Let's just get the number first. I missed a 22287. So units, right? To calculate the slope, it's rise over run. So I would take the units of my y-axis over the units on my x-axis, and that's going to give me the units of my slope. Log values don't have units, so I have no units on my y-axis. My x-axis are 1 over temperature. So what I essentially have is 1, because I don't have units for my y, over 1 over my temperature, right, in Kelvin, so 1 over Kelvin. And I would invert and multiply, so my units on my slope are actually just in Kelvin, right? 1 over Kelvin is just Kelvin. That's then equal to my negative of my activation energy. So those two negatives are going to cancel each other out, divided by my gas constant, 8.314 joules per mole Kelvin. So we're just going to take my slope, multiply it by my gas constant. Kelvin is going to cancel, and we're going to be left with joules for moles as my units. So I'm grabbing my calculator, and I'm typing these in. And I end up with, we'll have to round here in a minute, 185,294, it's a comma, joules per mole, which is our correct unit for energy. I am going to round. I need, I guess, 4 significant digits here. Actually, before I say that, let's go back up. Our significant figures actually need to come from our original values. So I do really only want 3 significant figures, sorry, I'm getting tongue-tied, in my final answer. I'm also going to convert it to kilojoules because this is such a big number. So I'm just going to move my decimal place over 3. Remember that there is 1,000 joules in 1 kilojoule. If you do need to go back and review metric system conversions, please do that. I'm going to assume, since this is general chemistry 2, you remember all of that from general chemistry 1. So 1,000 joules in a kilojoule. I'm going to end up with 185 kilojoules per mole as my activation energy. I'm going to give us one more version of the Arrhenius equation, and both the version that I'm about to give us and this one up here, let me actually circle it, are on your equation sheet, so the back of your periodic table. So you don't need to memorize these. So this is on your periodic table, and the one I'm about to give you is also there. This first one here is not, but I'm not going to ask you to use it. So that is the original form of the equations. I wanted to show it, I wanted to talk about the parts, but then in a form that's more useful to us, both of these are on our table. So this one, and then the one I'm about to give us. So scrolling back so we have some space. Essentially what we're doing with this last one, so natural log, is we have 2 data points. So instead of graphing something, we can just use the 2 sets of data. So let's actually write a heading. So another version. And this we're going to use when we have 2 data points. The one before we said is better if you have 4. If you have 3, use the other one. I'm not going to give you 3, so you don't have to worry about that. But if you only have 2 data points, this is the version we're going to want to use. So natural log, because I have 2 data points, I have 2 rate constants, so K1 and K2. And again, it's the natural log of that fraction, so you do need to take the fraction first. Don't take the natural log of k1 and divide it by k2. Don't take the natural log of k1 and divide it by the natural log of k2. Both of those are going to get the incorrect answer. So figure out that fraction first, take k1, divide it by k2, and then take the natural log of it. That's going to be equal to my activation energy divided by my gas constant, still the one that has units of energy as part of it. Again, that constant is on the back of your periodic table, but be careful to use the correct one because the other version, the one that's in terms of liters atmospheres per mole Kelvin, is also on your table. Multiplied by 1 over T2 minus 1 over T1. Our temperatures still need to be in Kelvin. So everything we had said before still applies. Temperatures in Kelvin, use the correct gas constant. Be really careful on this one too, that you're plugging in the right temperatures and the right constants in the right spot. So don't get like T2 paired up with K1, make sure you keep them straight. I see a lot of that because in this part here where you're subtracting, you're putting 2 before 1, but then in this part where you're dividing, 1 is on top and then 2. And a lot of times it's really easy to, like, if you do 1, oops, I didn't mean to do that. If you do 1, 2, then to do 1, 2, which is wrong. So just please be attentive to when you're plugging these numbers in. An example. So if the activation energy of a reaction is 185 kilojoules per mole. So the activation energy from our previous example. We want to know what is the rate constant at 325 degrees Celsius if the rate constant is 3.52 times 10 to the negative 7th molar to the negative 1 seconds to the negative 1 at 555 Kelvin. So we have two sets of data, right? I have a rate constant at a particular temperature, and then we're asked to solve, right, the rate constant at a different temperature. It doesn't matter which one you're going to make the ones and which ones you're going to make the twos, but it does matter that you keep them together. So just be really careful. What I like to do is take them out of the problem and make a list. When I do that, I'm more likely to plug them into the correct spot. If I just take them from the problem, it's really easy to get them goofed up. So I'm going to make these my ones. Again, if you want to make those the twos, you can. So this is going to be K1 and T1. If you want to make this K2, make this K2. So, or T2. Again, if you want to make those ones or twos, it doesn't matter, but you have to keep the pairs together. So the rate constant at this temperature. So whatever number you make those, make sure you make them the same. And then we're solving for the rate constant at a different temperature. So I'm going to make a list. I know that one of my rate constants, 3.52 times 10 to the negative 7th molar to the negative 1 seconds to the negative 1, goes with a temperature of 555 Kelvin. So again, I made those the ones, the pair that's given in the problem. I usually do. If you wanted to do the problem at the same time as me and make those twos, we're going to end up with the same answer. Long as we're here, just a quick review. Based on the units on my rate constant, what is the order of this reaction? Remember we said we could tell the order based on the units. Do you guys remember that? If you're thinking second order, you're correct, right? Remember we said our rate constant units for first order reaction were 1 over a unit of time. So seconds to the negative 1, hours to the negative 1, whatever that unit of time happens to be. And that our units for a second order reaction were 1 over molar seconds or molar unit of time. So this is a second order reaction. And then continuing here, K2, that's my unknown, that's what we're going to be solving for. And then its corresponding temperature, 325 degrees Celsius. We do need to convert that to Kelvin, so I'm going to add 273 to it. And when we do that, we get 598 Kelvin. So do remember that our temperatures need to be in Kelvin. Our activation energy, 185 kilojoules per mole. And then our gas constant, R, 8.314 joules per mole Kelvin. So we do have another problem here. What's our issue? Hopefully you're seeing that this is in terms of joules. Activation energy is in terms of kilojoules, so those need to have similar units. So I can convert my gas constant to kilojoules per mole Kelvin, or I can convert my activation energy to joules per mole, which is what I'm going to choose to do. So remembering that there's 1,000 joules in 1 kilojoule, when I convert this, I get 1.85 times 10 to the 5th joules per mole. Just a real quick way, it's kind of a review. Again, there's, right, 1,000 is the same thing as 10 to the 3rd. So if I wanted to multiply this number by 1,000, this is how I did this. I just did it in my head. I have 185, right, times 10 to the 3rd. It is now at this point converted to joules per mole. That would be correct. It's just that it's incorrectly written. Remember, scientific notation, I can only have one digit before that decimal point, and here I have 3, so this is not how it's correctly written. So if I want to put this in correct scientific notation, which I do, I would have to move the decimal point to here. So I'm going to move it 2 places, right? I'm going to move it by 100, 2 of the 10 spots. So because, and it's getting smaller, right? I'm going from 185 to 1.85. So because this is getting, because this is getting smaller by 100, right? Get smaller by 10, get smaller than by 100. And I don't want to change my number. I just want to write it differently. This is going to have to get bigger by the same amount. So if this got smaller by 100, then this has to get bigger by 100. So it becomes 10 to the 5th. I think it's good to be able to do these things in our head. Too often we rely on our calculators when we don't need to. And then also it's really easy to just type it into your calculator incorrectly, something like that. Just save yourself those mistakes. Okay, I have everything now, so we can just plug it into our equation. I'm gonna just copy this down so it's all on the same screen here. Oops, I didn't mean to do that. Trying to copy it for us. Just so we don't have to keep scrolling back up so much. Okay, so let's plug everything into that. The natural log of K1, 3.52 times 10 to the negative 7th over my unknown equal to 1.85 times 10 to the 5th divided by 8.314 joules per mole Kelvin multiplied by this fraction. So T2, 598 Kelvin minus 1 over T1, 555 Kelvin. So please, I want you to do this math on your own. So hit pause. When you're ready to check your work, hit play again. I'm actually going to do it in a couple parts. I'm going to do this part and then do the kind of the last part together when I work it out. So go ahead, try working it all the way through and then hit play when you're ready again. Okay, hopefully you guys gave that a shot. So I'm gonna do this part in my calculator and then multiply and divide by those numbers. So on this side, I got a negative 2.88, and then that's still equal to the natural log And again, remember it's the natural log of that fraction. So at this point, I need to undo my natural log, right? So I need to take the anti-natural log of both sides. So to do that, remember we raise it to e. So on this side, I'm going to have 3.52 times 10 to the negative 7th, divided by k2 equal to e raised to the negative 2.88. So our anti-natural log. So let me do that. And when I do that, I get 0.05, I guess 96. We'll just carry out an extra digit for now. I'll round when I'm done, but I do only want 3 significant digits in there. Finishing it up, I get that K2 is equal to 6.29 times 10 to the negative 6, molar to the negative 1, seconds to the negative 1. Unit-wise, let's go back and take a look at this real quick. At this point, I don't have units. So my joules per mole canceled with my joules per mole. And then these kelvins ended up canceling, right? 1 over Kelvin minus 1 over Kelvin is 1 over Kelvin. And then that 1 over Kelvin is multiplied by Kelvin, right? It's actually multiplied by 1 over Kelvin, which is the same as Kelvin, right? Invert and multiply, so those cancel. So I have no units here. So again, unitless, and then I end up with 3.52 times 10 to the negative 7th, molar to the negative 1, seconds to the negative 1, divided by a number that doesn't have units. We're going to end up with those units.